Hello everyone, and welcome to this video on section 5.4 called Comparison Tests. In this video, I'm going to be taking you through a preview version of a Newton-Alta assignment for section 5.4 on comparison tests. Please understand that in this video, the questions that I see may not be the exact same questions that you see when you work on the assignment yourself, but the objectives are the same, and hopefully the questions are similar enough that watching me do them here will help you when you work on them on your own. All right, so here's our Newton-Alta assignment page. You see the title of the section in the upper left without the word preview. In the upper right corner, you have the mastery bar, which shows you how far along you've gotten, your activity log, which shows you all the objectives and your progress in each objective. It looks like there are 3 objectives here. And back to the main page, you have a current objective, and then beneath that, a question related to that objective. And at the bottom of every question, you have a feedback button. So if you see any typographical errors or any issues with the answers or answer explanations, you can send feedback directly to Newton, and hopefully they'll get back to you about it and fix things. You will not have this instructor cheat button, right? This is for instructors only. But you will have a more instruction button. So if you're ever struggling with a topic or a question, click on this and it will take you to a page with further reading to do or videos to watch or both. And then it'll give you questions related to that instruction. And you can, every time this button comes up, click on it and work through the assignment that way. You can do this every single problem. And there's absolutely nothing wrong with that. Okay. So, the first objective I'm seeing here, use the limit comparison test to determine if a series converges or diverges. All right, so before I get into this example, let me talk about what this means, right? What is the limit comparison test? All right, so we're talking about now this is a test for infinite series, to determine whether or not the series is convergent or divergent. Now this is specifically for a series, infinite series with non-negative terms, or series that are eventually non-negative, like maybe if there are a finite number of negative terms, you can pretty much ignore them. If they're eventually non-negative, from some n onward, we could apply the limit comparison tests, but we'll just stick to saying that they have to be non-negative series, okay? All right, so limit comparison test. So suppose we are given 2 infinite series, sum from say n equals 1 or some integer to infinity of the terms of some sequence called a sub n. And another series, sum from n equals 1 to infinity of the terms of some other sequence called b sub n. All right. and we'll have them starting at the same point. Now again, these could be 1 or 0 or some other integer, capital N, but as long as they're going from some integer out to infinity. And like I mentioned earlier, these two series have terms that are non-negative, right? So all the a's, all the terms of this series are non-negative, or all little n greater than or equal to some capital N, right? So eventually, again, like I said earlier, eventually non-negative. Um, for the most part, though, we'll see our series with terms that are non-negative from the get-go. From n equals 1 or n equals 2. Same thing for the b sub n's, all right? So I have two series with terms that are eventually non-negative terms. All right. Well, then what we do is we look at the limit of the ratios of these corresponding terms. What happens to the ratio of an and bn as n goes to infinity, as you go further and further down the series? Okay, so then we look at the limit as n goes to infinity of the ratios of these terms, a sub n over b sub n. Now, I'm going to call this, well, let's just take this to the next page. We'll look at three different cases. All right. So one, if this limit is some positive, because again, these will eventually, as n goes to infinity, right after some point, these are non-negative numbers, right? So this would be some positive, 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 positive thing, right? So if this limit equal to, say, L, and L is some positive value that's finite, right? So between 0 and infinity. It's not an infinite limit. It doesn't have a limit of 0. So some positive finite value. Then both series will converge, right? These series we were given, or both diverge. Then both sums that we were given initially both of these converge, or both of these series diverge. So that's if the limit is a finite non-zero value. Right. And the reason for this is by direct comparison. We'll see a direct comparison test later, but I might as well talk about it right now. So remember, if a sequence converges, right, if I take these ratios here, a sub n over b sub n, and they converge to, say, some number that's positive, that means eventually, eventually, a sub n over b sub n will be between some positive values, say lowercase m and uppercase m, where both these are positive. Because again, we're approaching some positive value, right? Let's say for large n, right? For large n. Eventually, all the terms of this sequence are falling between these two. And again, the b sub n's here are positive terms. We multiply through by b sub n, and we get this. And again, m and little m and big M are just constants. And then we see by comparison, if the series of the a terms converges, well then, these are bigger than some multiple of the b sub n's, so the b sub n's must also converge as well, right? If a series of larger terms converges, then the series of smaller positive terms will also converge. This is the comparison test. I'll write this out more formally later. So they'll both converge. Now, if a sub n diverges, and then this series of larger terms, some multiple of the b sub n's, would also diverge. And if a constant multiple of something diverges, the series diverges. So like, again, a series of terms diverges, a series of larger terms would also diverge. So again, by comparison, we could say that either both are convergent or both series would have to diverge. All right, so that's part one of this limit comparison test. Now, what about the cases where the limit is zero or the limit is infinite? All right, so that's case two for this limit comparison test. Right, so if the limit as n goes to infinity of these, ratios of a sub n to b sub n, right, if this limit's zero, well then again you'd have for large n, well, shouldn't say for large n, just we'd have a sub n over b sub n. That sequence would be bounded because it is convergent, right? Remember what it means to be bounded, right? If some sequence is convergent, right, this sequence of ratios here converges to zero. Remember, if a sequence is convergent, then it is bounded, right? So a sub n over b sub n, again, would have to be between some m and capital M, but because the limit's zero, right, and these are all like positive terms, non-negative terms, let's put zero down here. And then multiplying through by 0 sub n, we'd get a sub n is less than or equal to some multiple of b sub n, right? Which would make sense, the term, if this limit is 0, that means the terms of a sub n are getting smaller, or they're growing at a slower rate than the terms of b sub n, right? The denominator would be growing faster than the numerator. So then if b sub n converges, a sub n must converge by comparison, right? If the faster growing terms are converging, then the smaller, slower growing terms would also be convergent, right? But that's all we can say. So if the limit is zero and we know the denominator sequence has a convergent series, right? So if this limit's zero and you were to take the infinite series of the denominator sequence, and that's convergent, then the numerator, because it's growing more slowly, we have smaller terms, would also be convergent by comparison, right? So then, with some of the numerator terms, the sum of that numerator sequence, would also be convergent. Now be careful with this one. It's not the other way around. If this limit is 0, then you know the numerator converges, that's the a sub n's, right? Adding up all these a sub n, the smaller terms. If you know a smaller series converges, you really can't say anything about the larger one, about the b sub n's here. So this is all we can make. This is the only time we can make a conclusion if the limit is 0. Now the other way around is, what if the limit is infinity, or the other extreme? So if this limit and approaches infinity of the ratio of these terms, if this is infinite, and again, these are non-negative terms here, an and bn, eventually, all non-negative. Well, if we're going to positive, if this limit's positive infinity, that just means the numerator terms are growing much faster than the denominator terms, right? In other words, a sub n over b sub n, right, will eventually be greater than any positive number you can think of, right? Take a capital M again. The limit's going to infinity, so this a sub n over b sub n, will eventually, for some n, large n greater than or equal to capital N, the sequence term, the a sub n over b sub n, will eventually be larger than any positive number you choose. And then multiplying through by b sub n again, we can get another comparison, right? So now here we can say, if b sub n is divergent, right, the series that's growing more slowly, then of course m times b sub n would also be divergent. And then we'd have the smaller terms are diverging here, and then the larger ones must also diverge, right? So if this is the case, and the denominator, right, the sum of the denominator sequence is diverging, then the numerator sequence must also diverge when you add them up. So yeah, so three different cases there. One that just tells us if things diverge, one that just tells us if things converge, and one that tells us if they both converge or diverge. Now, oh yeah, I forgot to mention, be careful with this last one too, right? If the limit of this ratio of your sequence terms is going to infinity, you can only say something, if the denominator sequence terms, the b sub n's, right? If they're diverging, then m times b sub n diverges, so the larger one's a sub n would also diverge. If the b sub n's converge, you can't, again, if a term of smaller stuff converges, you can't really say what the larger sequence is doing, right? So the larger a sub n sequence, the infinite series of those terms could converge or diverge. You don't know. That's just like the second case here, when the limit was 0. There's only one scenario where you can make a conclusion, a valid conclusion. All right, so I'm going to recap this one more time here. I know you can go back and back in the video and look at it again, but let me just recap this and then we'll get finally to our first example. So given two series, the sum of the terms of some sequence A and the infinite series of terms of some sequence B, and they're non-negative, right? Eventually non-negative. We look at the limit of the ratios of the sequence. What happens is A sub n, take every A sub n divided by the corresponding B sub n, see what happens to those ratios as n goes to infinity. So I take this limit. If this limit is between 0 and infinity, right, if it's finite, then both infinite series will converge or both will diverge. If the limit is 0 and the denominator series, or if you add up the terms of the denominators, the denominator of the A sub n over B sub n, you add up the B sub n's and they converge, then the numerator series must converge as well, right? Some of the A sub n's. And finally, if your limit is infinity and the denominator terms are diverging, then the numerator terms must also diverge when you add them up as well. So yeah, those are the three cases, three scenarios when we're doing this limit comparison test. All right, so back to the finally, right? Back to the example we were given. They're giving us a couple series and asking us to compute this limit. All right. So it's just going back to like Calc 1 stuff, finding limits of ratios. And so we're given the sum from n equals 1 to infinity of 2 over 9 to the nth power minus 8. And another sum from n equals 1 to infinity of just 1 over 9 to the nth. And we're calling the terms of this series the A sub n's, and of this series the B sub n's, right? And let's see what the limit as n approaches infinity of A sub n over A sub n is. Well, that'll be the limit as n goes to infinity of, the A sub n. The terms of this series look like this, 2 over 9 to the nth minus 8 divided by, and then the terms of, the B sub n's, the terms of this other sum look like this, 1 over 9 to the nth. Now multiplying by, dividing by 1 over 9 to the nth is the same thing as multiplying by 9 to the nth. So this would be the limit as n goes to infinity of, 2 over 9 to the nth minus 8 times 9 to the nth. So you'd have 2 times 9 to the nth power in the numerator, and then 9 to the nth minus 8 in the denominator. And then I hope you see that it would be basically just like having this limit here, right? Just the numerator be going to infinity, the denominator be going to infinity, but this minus 8 really doesn't have much of an effect when n is getting gigantic. So this is just 2, right? 9 to the nth over 9 to the nth would go away. This limit should be approaching 2, which is finite, right? It's not an infinite limit, and it's not 0. So remember, that was that first scenario, the first case of this limit comparison theorem. So by the limit comparison, both these series will converge or both will diverge. Now look at this series of the b's here. To be a ninth plus 1 over 9 squared plus dot dot dot. This is a geometric series. All right, this is one of those geometric series where, and then, to get from one term to the next, you multiply by 1/9, right? You just increase the power on 9 here by 1. The common ratio is 1/9, which is between -1 and 1. So this series is convergent. We've seen plenty of series now, and remember, geometric ones are nice. If you have a geometric series with a common ratio between -1 and 1, it will converge. And since I know this is convergent, and by this limit comparison test, the series of A's here, this first sum must also converge, right? So both series converge. Now, if this other series was divergent, I would say they both diverge, right? Again, if this limit of A sub n over B sub n, if this limit of these ratios is finite and non-zero, then both series are going to converge or both series will diverge. Okay. Now that's not what they don't want us to conclude that here. Now let me actually show you the convergence, right? Now we know what this converges to. This would converge to, 1/9 divided by 1 minus 1/9. So this converges to 1/8 or 0.125, right? If you add more and more terms onto this, it should get closer and closer to 1/8. Let me show you that here in the Desmos calculator. Let me blow this up a bit. So if I do the sum, we'll say 1 to x of just 1 over 9 to the n, and make a table here and put in higher and higher values of x. The first term is 1/9, the sum of the first 10 terms, 100 terms. So you see, eventually, it's so close to 1/8, it just says it's 0.125. That's 1/8. All right. Now, look at the other series. So we saw this was convergent to 1/8, right? Now the other series, it won't converge to 1/8 necessarily, right? Just because we're comparing them doesn't mean they're going to converge to the same value, but they're similar enough to where if I know one converges, I know the other one should converge as well. This was the other series we were given, and I'll make a table for this. The first term of this would be 2 over 9 minus 8, 2, right? There's the first term. See some of the first 10 terms, 2.0305 something, some of the first 100 terms. And notice after a while, the decimal's not changing. So I've got at least the first 6 decimal places here. This last one might be rounded. But this is converging to 2.030514 something. But I can see after adding up the first 100,000, 10,000 terms, we're approaching some finite value, right? This series also converges. Now it definitely doesn't converge to 1/8, right? That's the series we were comparing it to. But by that limit comparison test, I know that the one I'm comparing it to converges, and this one must converge as well. We can see that here. Right, now back in the problem, though. Right, back in the problem, all they wanted was that limit, and we said that limit was 2, right? The a sub n over b sub n as n goes to infinity. That limit should be 2. And they run that through here. Now they don't explain anything after that, but like I was saying, since this limit is non-zero and finite, both series, converge or both diverge. And again, we know one of them converges because of the whole geometric series thing. So the other one must converge as well. Great. Okay, so now this is just a simple comparison test. Now you can do limit comparison just as easily as you do comparison. I actually find limit comparison to be a lot easier to work with. But let's go through here. Now they're only asking you, what series would you compare it to? You saw in the last example, I did a limit comparison with a geometric series, right? Geometric series are nice. You know when those converge and when those diverge, those geometric series. Another nice series to compare things to quite often is p series, right? The sum of 1 over n to the p, like 1 over n, or 1 over n to the fourth, or 1 over n to the third, like all these here. Because remember, a P series will converge when the power on n in the denominator is greater than 1. So this is divergent, this is convergent, 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 right? So, and then when it's less than or equal to 1, it diverges. So yes, quite often we'll be comparing to a geometric series or one of these P series. So let me write out what the comparison test is, right? Now I've already explained it a little bit in the limit comparison test, but here's just the comparison test for series. So yeah, with limit comparison, you just needed some series with eventually non-negative terms, right? And then you did what happens to their ratio as n goes to infinity. For the direct, sometimes this is referred to as the direct comparison, right? Because you got limit comparison. People might get confused if you just call this comparison. So we'll do a direct comparison. So again, say we're given a couple series, right? Sum from n equals 1, or some integer to infinity of a sub n, and another series again called the sum from 1 to infinity of b sub n. And these terms are eventually non-negative, right? So and they also satisfy the following inequality. So there's a little extra to this. Not only are these non-negative, but one series has terms that are eventually smaller than the other one. So let's say the terms of A end up being smaller eventually than the terms of B. So I got this inequality here, right? For all n eventually, right? For all n greater than or equal to some capital N. So that's the setup. So we're not taking any limits or anything. And if this is the case, right, the terms of these series are eventually non-negative, and eventually the terms of A are all smaller, or at most the terms of B. And I've explained these a little bit when I was doing limit comparison. If the series of smaller terms, right, the n's diverge, then the series of larger terms will also diverge because they're even larger, right? If the smaller series diverges, then the series of larger terms must also diverge. In the other case is, well, if the series of larger terms converges, then being smaller, right, the series of smaller terms must also converge, right? So if the larger series, right, so the B's here, if that series converges, then the smaller series must also converge. That's it. Now you got to be careful, all right? If the smaller series converges, you really can't say anything about the larger series, because it could be too large where it diverges, or it could be small enough, close enough to A where it converges, but you can't tell. Also, if the larger series, the series of larger terms, uh, diverges, then you can't say anything about the smaller terms, the series of smaller terms, because they might be small enough where they converge. So this is it. This is the only two times you're going to be able to actually make some valid conclusion. So now, the the example we're looking at from the problem here. we're given this series. So sum from n equals 1 to infinity of, and then the terms of our sum look like this, n over 3n to the fourth plus 5n cubed plus 4n, right? So again, the terms of this series, right? The terms look like this, right? N over 3n to the fourth plus 5n cubed plus 4n. As n goes to infinity, right? The further and further down the line we get, these terms would be like, again, I say like, they're not exactly the same, but remember with polynomial stuff, right? When you're letting the value of the input go to giant lengths, getting them larger and larger, the numerator is still going to be that, the lead term of the numerator is still n. In the denominator, right, you got this n to the fourth power term. That would dominate the lower power terms. So eventually, the 3n to the fourth power is so much bigger than these are practically nothing. Not very technical way of doing this, but you remember, you just look at lead terms of polynomials when you're discussing what happens as the input gets larger. And this reduces to 1 over, 3n cubed. So that would be a good thing to make a comparison to. Let's compare our series to this series. Now, this is actually just a multiple of a p series. Now, I'll get a little inequality going on here. The terms of this sum, n over 3n to the fourth plus 5n cubed plus 4n. Since n is 1 or greater and there's a bunch of addition here, this will always be positive. Right? This will never be under 0. And if I took away these values here, well, these are positive. These are also positive values. If I were to take these away, you make the denominator smaller. And one little note for you, making a denominator smaller makes a number bigger. Right? Making denominators smaller increases the value. For example, if I take 1/3, this is 0.3 repeating, right? 0.333. If I make the denominator smaller, make it 2 instead of 3. You see how this is 0.5? That's bigger. So that's just one little example. So if I do that, these are positive terms. If I take them away, I make the denominator smaller, which will make this bigger. And of course, this is for, n greater than or equal to 1 at the moment, right? We're starting at 1. These are all positive terms starting at 1. So if I take these away, we'll get something larger, over 3 to the fourth, which is, 1 over 3n cubed. And I could also get rid of the 3, which would make this denominator smaller, right? Multiplying by 3 is bigger than multiplying by 1. And if I turn this 3 into a 1, that'll make the denominator smaller, which makes the whole number bigger again. So this is less than 1 over n, just 1 over n cubed. And we can compare to this. So comparing to 1 over 3n cubed is very much like comparing to 1 over n cubed, right? This is just a multiple, 1/3 of 1 over n cubed. Now, all the terms of our sum are less than these, and we know that the series of these terms, right, the sum from n equals 1 to infinity of 1 over n cubed converges, right? This is one of those convergent p series, right? The power on n down here is greater than 1. And therefore, by comparison, right, see this, the series of larger terms converges. So this series of smaller terms must also converge, right? So by comparison, our series, right, the series of smaller terms must also converge. I'll say converges here. But that's not what they're asking. They're just asking what should we compare to, and that would be this sum of the 1 over n cubed. Again, just take your terms and think about what they would be similar to as n goes to infinity. What would they be like very much close to or like? And they'd be close to this 1 over 3n cubed, which is just a multiple of 1 over n cubed. So we could do a nice comparison to the sum of 1 over n cubed. Right, so that's this third choice here. And that's all they're asking, right? Yeah. And they do the same kind of inequality deal that I did, or they have less than or equal to, but yeah. All right. All right, so now we have both comparisons tests, the direct comparison and limit comparison. So now the rest of these problems should be involving one of those two things. All right, so here we're use a comparison test. Notice it says use a comparison test. So it could be the direct comparison or limit comparison. Now I mentioned this earlier, right? Direct comparison's fine. Now if you can see a nice geometric series or a p-series to do a direct comparison with and be able to get to one of those two cases, great. I personally like using limit comparison because I think it's easier. You don't have to set up nice, you don't have to think about inequalities too much. When you're doing limit comparison, you're just taking a limit of some ratio. So for most of these, when they say use a comparison test, I'll be choosing to do a limit comparison. And we should do a limit comparison to, some series we know something about. So our geometric series or, p-series. Those are the two typical ones that we know something about. All right, so look here, we've got for what values of p does the series below converge? All right, so we have the sum from n equals 2 to infinity of the natural log of n over 40 n to the p. All right, so what I'm going to do, we'll do I'll write this up. Equals 1 to infinity of, we have natural log of n over, and then 40, times n to the p power. So let me call these natural log of n over 40 n to the p, call these a sub n. Right? And then what I'm going to compare this to, I'm going to do a limit comparison. Like I said, I prefer limit comparison to direct comparison. Let's do a limit comparison with, something that's very similar to this. All right, something very similar, which after a bit, I'm going to say that this is very similar to just, something over n to the p. Right? Actually, yeah, if I do that, that'll be a bit of a problem. Yeah, because all right, let's see what happens. Let's see what happens. Let's see if I just do a limit comparison with something like that, just a p series. We might need to change this up because the numerator of this is not a constant. This is a constant. So I might change this up in a little bit, but we'll see. I'm going to play around with this. Let's see what happens. So let's call this 1 over n to the p b sub n. And let's look at the limit as n approaches infinity of, the a sub n over, oh yeah, this is from n equals 2 to infinity. And see what happens to the ratios of these terms. This will be the limit as n approaches infinity of, the natural log of n over 40 n to the p, but then, divided by 1 over n to the p, so that'd be times n to the p, and you see the n to the p's cancel. And this would be infinite, okay, which they're asking me about convergence. So remember this case here, when the limit was infinity, if the denominator series diverged, the numerator series diverged. That was really all we could say in that third case of the limit comparison test, right? When the limit was infinite. So, when the sum of the b's diverges, the sum of the a terms, the numerator terms, also diverges. But again, that's all we could say when the limit was infinite. Well, these diverge, when p is less than or equal to 1. Right? So I know for a fact p's got to not be this. Right? Because if p is less than or equal to 1, then, this series will diverge, and so will this. Right, so we know at least, all right, so from this, so we got some information out of this. So we know now that at least, all right, I don't know if this is going to be working out, p needs to be greater than 1. But there's no guarantee. And when p is greater than 1, the p series converges. But remember, when the limit's infinity, just because the denominator series is converging, you can't say anything about the numerator series. All right, so I got to do a little bit of a different comparison here. Maybe a direct comparison wouldn't be terrible. So from the limit comparison with this p series, I can tell that I know that p needs to be at least 1, right? Greater than 1. Right. Now, does it have to be higher though? Again, I can't say anything from this limit here. Now, the natural log of n, for n greater than or equal to 2, right, when we're 2 or higher, if you look at the log function, that is log of x, right, your natural log function's doing this, and that's actually smaller than just x all the time. Y equals x grows much faster than natural log of x. So definitely from 2 onward, the natural log of n, well, first off is, positive, because there are going to be positive terms here. And this is always less than just n. Ah, okay, so I see where we can go with this. So if I divide both sides of this by, 40 n to the p, then it's 2 or greater, so this will be some positive number. So we can do a nice, actually, direct comparison. How about that? So I divide both sides here by 40 n to the p, and being positive, it won't flip the symbol or anything. So we're getting the terms of our sum, right? This natural log of n over 40 n to the p will be less than, or you could say less than or equal to, is still the same direction. And then this simplifies to 1 over, 40 n to the p minus 1. Right, which, like I was doing earlier, if you want to change the 40 into a 1, that'll make the denominator smaller, which will make this number bigger. So just 1 over p to the n to the p minus 1, sorry, that's n to the p minus 1. So if we do this direct comparison, remember this series here, the sum from n equals, say, again, 2 to infinity we're doing, of 1 over n to the p minus 1. Right? This is a p series, but the power is, p minus 1. But remember, for these 1 over n to a power, that power, this will converge when the power, right, when p minus 1 is greater than 1. So p must be greater than 2 then. That's more like it. Right? When p is greater than 2, the series of these terms, these larger terms will converge, and then by direct comparison, smaller term series will also converge. Yeah, so this is got to be greater than 2. Yeah, if it equals 2, then this series will diverge, because you'd have 1 over n to the first, just 1 over n. That series is a harmonic series, right, which diverges. Now, having a larger series, a series of larger terms that diverges doesn't say anything about the smaller one. So, from my limit comparison earlier, yeah, I know that this has got to, p's got to be bigger than 1, but we added to that saying, hey, by direct comparison, p's got to be greater than 2. Could p be equal to 2? That's the question. It says here, p less than 2, obviously not. P greater than 2 is what I just stated. When p equals 2, what happens? Let's go back. If p were equal to 2, you'd have natural log of n over 40n squared. Natural log of n over 40n squared would be less than or equal to n over 40n squared. 40 over n. Yeah, again, being less than some divergent series doesn't say anything. Well, here's the thing though. It is a single choice value thing, so like you can't pick more than one. So it's we just showed that he has got to be at least greater than 2, and that's the only option here. Right, so p has got to be greater than 2 by that direct comparison that we did in order for this to converge. Right? And you see yeah, they do again a comparison test. Yes, exactly like I had written earlier. Great. All right, they did a nice direct comparison, just like I showed you. P has to be greater than 2. for our series to converge. Right, so this time they're saying use the limit comparison test. And they give us this P series. This is 1 over the square root of n, right? That's 1 over n to the half. Determine if the series below converges or diverges. So here's the series we're asked, does this converge or diverge? We have the sum from n equals 1 to infinity of 8 over, this is the square root of 25n. But I'm just going to write that as 5 times the square root of n, right? That's the square root of 25n, and then minus 2. I'll call these my a sub n's, right? And then we're going to do a limit comparison with and they gave us the series to do the limit comparison with, the sum from n equals 1 to infinity of just, 1 over, now the square root of n. Remember, this is n to the half power down here. So it's a P series where P is, less than or equal to 1. So we know that this is divergent, this series we're comparing with. Again, I'm gonna call the 1 over square root of n the B sub n's. So limit comparison is I'm taking the limit as n approaches infinity of the ratio of these terms, right? A sub n over B sub n. And this would be the limit as n goes to infinity of, 8 over 5 root n minus 2. And then divided by 1 over the square root of n, which would be times the square root of n. All right, you're going to put the square root of n in the numerator here. And you can see as n goes to infinity, this would be going to 8/5, right? These are the same power, these lead terms here. Which once again, we saw an example like this earlier. This is finite and not 0. So remember, when this limit is finite, some value that's, positive and not 0 or infinity, right? By the limit comparison test, both series converge or both series will diverge. And we already know that one of them diverges. So our series must diverge as well. Series of the 8 over 5 root n minus 2 must also diverge. Right? Yeah, so by limit comparison with the series they gave us, series diverges. Okay. All right, so this one, all right. So I'm going to just tell you, look back at the example. There was a couple examples ago where it was the sum from n equals 2 to infinity. It was the natural log of n divided by 40 n to the p. Having 39 instead of 40 here won't change anything. I do that same direct comparison where this natural log of n over n to the p would be less than or equal to 1 over n to the p minus 1. And so we'll get a convergent series when p is, greater than 2. So I'm not rewriting all that, right? This is incredibly similar to the first example like this with the 40 n to the p. So this p needs to be greater than 2 in order for this series to converge. And you'll see they're doing the same direct comparison that we saw in that problem. Okay. All right, so now which of the following series should be used to determine the divergence of the series? Now, if you were to, you got the square root of 3n squared plus 2n plus 4 up here. Remember, if you were to have n go to infinity, which you are, the square root of 3n squared would dominate, the 2n plus 4, which would be the square root of 3 times n over n. I mean, this is kind of silly that they're having us do like limit comparison or direct comparison here. These terms are approaching the square root of 3. All right, if you were just looking at the terms as n goes to infinity, these are approaching the square root of 3, which is not 0. You might recall from the divergence test in section 5.2 or 5.3, section 5.3. If the terms aren't going to 0, it's divergent. So it's silly, but we could do a limit comparison with 1 over n. If I divided these by 1 over n, you'd get the n's canceling, and then this would go to infinity. The a sub n over b sub n would go to infinity. And remember, if the limit of that ratio is infinity, when the denominator term series was divergent, the numerator would diverge as well, and this would be the numerator. So I would compare to this 1 over n. And this is I don't like this because the terms of this series aren't even going to 0. So there's no point in doing a comparison test or limit comparison test or integral test or any of those tests. If the terms aren't going to 0, the series is divergent. So of these choices, the only other divergent series would be the 1 over n, the harmonic series there. Now they run you through they're doing another direct comparison. But yeah, I don't care for that because they showed you that the terms are going to the square root of 3. They're not going to 0. So it's divergent, the end. There's nothing to compare to. All right, so back to a use of the limit comparison test. So use limit comparison with the geometric comparison. All right, here's a geometric series. I'll write this out to determine if the series below, converges or diverges. So the series we're asked about is this series here. I've got the sum n equals 1 to infinity of 9 to the nth power, then plus 9 in the numerator divided by then 2 to the nth. So again, I'll call these the a sub n's, right? The sequence a that we're adding up. And we're going to compare to, I'm doing a limit comparison to the sum from n equals 1 to infinity of just 9 to the nth over 2 to the nth, which is 9 halves to the nth. The first term would be 9 halves, then 9 squared over 2 squared, then 9 cubed over 3 cubed, right? Over 2 cubed, sorry. This is one of them, geometric series. They even told us it was geometric. And the common ratio here is 9 halves, right? You would multiply the numerator by 9, denominator by 2 every time to get from one term to the next. And this, unfortunately, this is greater than or equal to 1, right? That's 4.5. Remember, if the common ratio is not between -1 and 1, you have a divergent geometric series. So I know that my sum of the b sub n's, what I'll call the 9 to the nth over 2 to the nth of b sub n's, I know this sum is divergent. Right, so that might help me later. So let's take a look now at the limit of the ratio of these corresponding terms, right? The a sub n's over the b sub n's. Limit as n approaches infinity of a sub n over b sub n. Limit as n approaches infinity. Now, you'd have 9 to the nth plus 9 divided by 2 to the nth. Now, dividing by this, right, is multiplying by the reciprocal. So times 2 to the nth over 9 to the nth. And you can see the 2 to the nths canceling. And then basically you just have 9 to the nth over 9 to the nth, right? The plus 9 won't make a huge dent when n is getting larger. So this limit's 1. And once again, that is not 0 and finite, right? It is not infinite and it's not 0. So remember, when this limit of this ratio, right, was not infinite and it wasn't 0, remember that was the case, that first case where both theories that we're looking at converge or both diverge. And since this is divergent, our series must also diverge as well. So our series must also be divergent, right? Must diverge. Right. So by the limit comparison test, the series diverges. All right, moving on. All right, so this one is incredibly similar. So I'm going to leave this to you. I'm just going to describe it out loud. Instead of 9 to the n over 2 to the n, they got 8 to the n over 6 to the n. You know, so this series is geometric, right, with a common ratio of 8 over 6. Right, you'd multiply every term by 8 over 6, which is 4/3. That's bigger than 1. That's 1 or greater. So again, we have a divergent series. And if I were to take 8 to the n plus 8 over 6 to the n, divided by 8 to the n over 6 to the n, you'd have something where it was pretty much like 8 to the n over 8 to the n. The limit would be 1, which is, again, non-zero and finite. So they both converge or they both diverge. And like I said, this geometric series up here has a common ratio of 1 or greater, or -1 or less. It's a common ratio that's not between -1 and 1. So we got divergent here. This must also diverge then by the limit comparison test. Again, very, very similar to the example before this. So that objective's done. All right, and this is so again, look back through the video. I did one like this already. You got the natural log of n over, instead of earlier we saw 40 n to the p, or there was a 39 n to the p. Doesn't matter as long as this positive constant in front end of the p really won't affect anything. So, remember natural log of n divided by n to the p would be less than n over n to the p, which would be 1 over n to the p minus 1. And that series, a series of 1 over n to the p minus 1, will converge when p minus 1 is greater than 1. So when p is greater than 2, right? So again, very similar. There's been 2 other examples in this video, one long one and one very short one, where I did this already and found that p must be greater than 2 in order for this series to converge. So let's look back earlier in the video. And they're doing very much the same kind of comparison. So this one's a little different. All right, so for what values of p does this series below converge? All right. Okay, so we could try a direct comparison. We could try a limit comparison here. I'm going to write this out. Mess around with it. So we're given this series, right? The sum from n equals 1 to infinity of 14, which again, the 14 won't really matter all that much. Constant multiples can be pulled out, times the sine of 1 over n divided by, and then, n to the p. Now, you might recall something from Calc 1 involving sine of something over something. I'll write this up over here. This is just something I'm noticing. This would take experience to see, unfortunately, but the limit as, say, x approaches 0 of the sine of x over x. Remember, this limit was 1. So when I see the sine of something over something else with a variable. I like to try to think I can bring this into play somehow. So, n to the p, I'm going to try this out. I got the sine of 1 over n. To get something like this involved, I'm going to multiply the top and bottom by 1 over n. Now, if I do this, this would be, 1 over n is like having, n minus 1 times then the sine of 1 over n over, and then I got this n to the p factor down here times, and then, 1 over n. And n to the minus 1, again, times n times n. This is kind of like this now, where it's the sine of 1 over n over 1 over n, times, and then n to the p plus 1. Right? And as n goes to infinity, this, sine of 1 over n over 1 over n, the 1 over n is going to 0. This is going to 0. This is going to 0. Just like this, you have the sine of something going to 0 divided by something going to 0. So this would be approaching 1. Right? So as n goes to infinity, this thing will approach 1 over, n to the p plus 1. So this is what I'm going to compare to. I'm going to do a limit comparison. Because again, so what I'm saying is the terms of this will get closer and closer to the terms that look like this. I'm going to do a little limit comparison here. Right? So I'll call the original terms a sub n, call this b sub n, and we'll do the limit as, n approaches infinity. I basically kind of did this already, but let's watch, right? So let's take the limit as n goes to infinity of the a sub n over b sub n, which, limit as n goes to infinity. We have your 14 times the sine of 1 over n over n to the p, and then, uh, dividing by the 1 over n to the p plus 1 is multiplying by n to the p plus 1, which would cancel a lot of these n's, right? Would cancel all but one of them, right? You have n to the first up top. The limit as n approaches infinity of 14 times the sine of 1 over n times and then just n. But multiplying by n is the same thing as dividing by 1 over n. And you see this limit here is 1, so this limit's 14, which is not 0. It's not 0, it's finite. Right? So by the limit comparison test, both sums, right, both the sum from n equals 1 to infinity of 14 times the sine of 1 over n to the p, and the sum of these b sub n terms, and I call this b sub n, right? Sum from n equals 1 to infinity of just 1 over n to the p plus 1. Both will converge and both will diverge. Right. Now remember this, they're asking for values of p for which this converges. Remember this is like a p series here, 1 over n to some power. Right? Remember this converges when the power on n, so p plus 1 is greater than 1. So subtracting 1 from both sides, when p is greater than 0. So that's when both of these will converge, because when p is greater than 0, this will converge, and by limit comparison, this will converge as well. So p must be greater than 0. That's what I got down here. All right. So yeah, when you're doing comparison or limit comparison, when you're trying to think of, what series should I compare it to, and I think I mentioned this before, but think about what happens to the terms as you go out further and further. What happens to the terms as n goes to infinity? Well, I showed you that these terms here would approach terms that look like this. They're not exactly the same, but they would look something like this, or be very, very close to this. And if that's the case, then that would be a great candidate to do some sort of comparison with, either a direct comparison or a limit comparison. Right, yeah, and they do all that. Cool. All right, then determine if the series below converges or diverges, by comparing it to a p-series using the comparison test. So this is direct comparison. The sum from n equals 1 to infinity of 7 over the square root of 16 n squared, minus 2. So again, as n goes to infinity, right, the terms of this sum would approach 7 over just, the square root of 16n squared. The whole minus 2, they approach 0, right? The terms go to 0, but as n goes to infinity, the minus 2 down here wouldn't really have much of an effect. You'd basically have the square root of 16n squared down here, or 7 over 4n, right? So this would be a great thing to do some comparison to somehow. All right. Now for n greater than or equal to 1. All right, so n greater than or equal to 1, these 7 over square root of 16 and squared minus 2, these will be positive, right? These are positive, non-negative. Plug in 1, plug in 2, plug in 3. They'll be positive, but getting smaller and smaller, but they're positive, sure. Now, if I'd like compare this to this, remember I said like this minus 2 after a while kind of doesn't matter. It'll be almost negligible. Now, if I get rid of that, though, that's a negative number. This minus 2. If I get rid of this, getting rid of a negative in the denominator. So getting rid of this will make the denominator bigger, right? Because that'd be like adding 2 to this, which would make it bigger. So getting rid of a negative term, we saw in an earlier example, getting rid of positive terms is subtracting stuff. That makes you smaller. Getting rid of negative terms makes you bigger, right? We'll make denominator bigger. Bigger. And you might recall from, earlier example, when I made the denominator smaller, the value of the expression got bigger. But if you make the denominator larger, you make the denominator bigger, the value of the expression will decrease. For example, just take the reverse of what I did earlier. 1/2 is, 0.5. If I make the denominator bigger, make it 3 instead, well, that's 0.33, forever, which is smaller. The one I started with was bigger. Right? The value decreases when I make the denominator larger. So if I get rid of this term, it's going to make the value smaller. So the terms of our sum right now will be greater than or equal to these terms. Just get rid of the minus 2 there, which is, 7/4, 7 over 4n, right? And if you'd like, 7/4 is bigger than 1. So this is bigger than 1 over n. Right? 7 over 4 is bigger than 1. So you can say that's greater than or equal to just 1 over n. And then I can compare these terms to terms of 1 over n, And again, these are all for n equals 0, right? All these are non-negative for n equals 1 or larger. Well, what do we know about this series, right? We know that the sum from n equals 1 to infinity of 1 over n, right? This was that harmonic series, right? This is a p series with p 1 or less. This is divergent, right? And so we see that the sum of the smaller term series is divergent, meaning the sum of the larger term series must also diverge, right? So by comparison, right, by direct comparison here, this diverges as well, this sum that we were given, because all the terms of this sum are bigger than the terms of the sum, the 1 over n's. And, again, if the smaller term sum is diverging, the larger term sum, must also diverge. Right? So the series diverges by direct comparison. Right? Again, they run through that here, right? See, again, getting rid of the -2 down there makes the number smaller, right? It'll make the denominator bigger, which makes the whole number smaller. Great. So here, determine if the series below converges or diverges by comparing it to a p-series using the comparison test. Uh, okay, well, it says use the comparison test. Honestly, I would do limit comparison here, because again, I think it's a lot easier. Now I'll try to show the direct comparison, but I'll show you a limit comparison first. So we're given the sum from n equals 1 to infinity of this rational expression, 8n to the 7th. Again, I don't understand why they're doing this to you. 8n to the 7th, plus 2n to the 6th. Plus 3n squared over, and then 5n to the 5th minus 2n cubed minus n. Look at the terms, call this a sub n. The limit as n approaches infinity for these terms is infinity, which is not 0. So this is divergent. I mean, I don't like that they're saying use a comparison test. The terms of this sum aren't even going to 0. Right, the numerator, this is like having 8n to the 7th over 5n to the 5th, right, which would be like 8 n squared, which would blow up, get huge. So the terms of this sum aren't even going to 0. So yeah, this is definitely divergent. But I see that if you want to do a limit comparison, you know, I mean just look at the sum of just n squareds. Because again, these look like 8/5 n squared, so you get larger and larger. So if I compare to this, you know, have this be b sub n, and the limit as n approaches infinity of a sub n over b sub n, I hope you can see, would be 8/5, which is not 0, and it's finite. Because if I divide this by n squared, and make this 5 into the 7th and 2 into the 5th and n cubed, right? You'd have 8 into the 7th over 5 into the 7th, basically. So you get 8/5 for this limit, which is not 0 and it's not infinite. So both converge and both diverge, and this is definitely a divergent series. And I guess you could see this as the sum of 1 over n to the negative 2. 1 over n to the negative 2 would be n squared. So I mean, that would be the p series you're comparing to, and the value of p is definitely less than or equal to 1. It's -2, so divergent. Right? Yeah, this is a silly one. I don't. Now they're saying do direct comparison. So 8n to the 7th plus 2n to the 6th plus 3n squared divided by 5n to the fifth minus 2n cubed, minus n. Remember what I was saying earlier? If you get rid of negative terms, right, if you get rid of negative terms in the denominator, that's like adding, you're making the denominator bigger, which makes the value smaller. So this fraction here will be greater than or equal to 8n to the seventh plus 2n to the sixth plus 3n squared over, and then just the 5n to the fifth term. And then if I get rid of positive terms in the numerator, right, say I got rid of these are positive terms, right? N is 1 or greater, right? N is positive. Now, if you get rid of positive terms in the numerator, that's like subtracting from the numerator. That'll make the numerator smaller. And if you make the numerator smaller, you get smaller, right? So like 3/5. If I make the numerator smaller, 2/5, it's smaller. So I make the numerator smaller, it gets even smaller. And this would be, just 8/5 n squared, really. And again, this is greater than 1/8, so you could say this is greater than or equal to just n squared, and then do a direct comparison to the sum of n squareds. So like I said, just if you look at what happens to the terms as n goes to infinity, that'll give you a rough idea as to what you should do comparisons to, especially with these polynomial and rational expressions. And yeah, the sum of n squared is definitely divergent, and those are the smaller terms, right, which are positive still, and the sum of the smaller terms diverges, so the sum of the larger terms must also diverge, by comparison. Either way, there's multiple ways to look at this to say that this series diverges. Yeah, so you see the 1 over n to the negative 2 here. Ugh. Okay, all right, and that's it. All right, so you've seen the limit comparison test, the direct comparison test to, determine if a series, an infinite series of, again, eventually non-negative terms, right? Remember these tests here were really only for series of eventually non-negative terms. So now you have these tests under your belt, right? Comparison test, limit comparison test, to say whether or not certain series of non-negative terms converge or diverge. Now, all it says is whether or not the series converges or diverges, right? These tests do not tell you what the series converge to. If you want to figure out what a series converges to, you're going to have to look at your sequence of partial sums, keep adding on one more term at a time to get better and better estimates of what the series converges to. And, if it's a series of positive decreasing terms, then you can go back to section 5.3 and look at the integral tests and the remaining, there's a part of that section where we talked about estimating the values of series, convergent series. But again, that only applied to series of eventually positive and eventually, decreasing terms. Okay, so got these under. And like I said, at the top of the video, right, the questions I saw here won't be the same questions you see when you look at the assignment yourself, but hopefully they're similar enough so that watching me do them here, talk about them here, will help you when you work on the assignment on your own. And thank you very much for watching.